Hi everyone, hope you're doing well. In this lecture, we'll talk about the harmonic oscillator. It is one of the most important problems in quantum mechanics, and it's related to some very general problems. It allows to describe the interactions in a solid, the ionic interactions in a solid material. But the general problem comes from classical mechanics, all right? So let us talk about the classical problem first. So the classical problem, right? It just corresponds to the very simplified version of this problem, just corresponds to somebody of mass m here, which is linked to a rigid wall here. It is connected to a rigid wall by a spring of constant K. Say this is the spring constant. And this mass is allowed to move here, all right? Neglect all gravitational effects, neglect friction. So lossless or frictionless is the ideal harmonic oscillator. So it's perfect. The ideal case, which corresponds to the case without losses, because in general, in practice, in the classical system, you will have losses due to friction between this massive object and the ground. But suppose it's perfect and no friction is present in this problem. The force is suppose here we attach some reference system. So this is the x axis. Zero is corresponding to just the equilibrium position, and you can just uh, pull the mass, and you will oscillate, all right, in the x-axis. Suppose no motion is allowed in the y-axis, all right? So the motion is one-dimensional in this case. So we are just confining ourselves to a one-dimensional problem here. The forces exerted by mass corresponds to some minus kx. If you pull the mass a little bit to the right of the equilibrium point, there will be a spring restoring force which tends to pull back the object, all right? And if you push a little bit the object to the left, the spring will try to restore the object to the equilibrium position, all right? So there is a Hamiltonian which corresponds to some kinetic energy, p squared divided by twice the mass of that object. All right, so this is the Hamiltonian of the problem, corresponding to the kinetic energy of the motion of that mass, plus some potential energy. This potential energy is corresponding to the spring. It's provided by the spring and the restoring force. So this term here corresponds to the potential energy of this mass under the influence of this spring. All right. Well, if you calculate the Hamilton's equations, you'll find out that the derivative of the Hamiltonian with respect to the momentum, it is x dot, which means the time derivative of the position of the particle, right, is provided by Hamilton's equations. So if you just apply the derivative with respect to momentum here, you'll find out P over m, because this doesn't depend on the momentum, it's just position dependent term. This is the potential energy. And if you calculate the other equation, you'll find that the derivative with respect to x, the minus the derivative with respect to x, corresponds to P dot, which means dp over dt. All right, this is the time derivative of momentum. And this is the force, all right? This is the force acting in one dimension, so that's why I'm not inserting some vector notation here, because we are just considering one dimension here. So if you calculate here, you'll find out dx dt is equal to p over m. This is the first equation in the classical problem, and the second equation will be the time derivative of momentum corresponds to the negative of dh dx, and in this case you'll find out minus k times x. That's what we really need here, because this is the restoring force, and momentum varies according to the force. This is just the Newton's second law, all right? So it is a pair of equations, all right? So we can solve this classically, this problem. We can solve this classically. So consider taking the derivative of this equation here. So if you take the derivative, you'll find out a second order derivative of the position of the particle, but this is just 1 over the mass, the derivative of the momentum, all right? But the derivative of momentum with respect to time is just minus k times x. So we'll find minus k divided by mass here times position. So this is a second order equation. Second order equation plus k over m x. X is a function of time, which is equal to 0, because we are considering, given that there is an initial condition here, you do not apply any external forces. It's just the action of the restoring force of the spring. So you can just push the mass a little bit from the equilibrium position, and when you let the system oscillate, it will oscillate forever, all right? This equation has a easy solution, all right? So x as a function of time t can be written as some constant a cosine of omega t plus some constant b, the sine of omega t. And now you can just calculate momentum. So momentum is mass, the time derivative of the position, and you can insert two initial conditions. So x at time t equals to 0 is some x naught. Here it's the initial position, the amplitude which you just inserted in the system at t equals to 0, and the initial velocity of the system is equal to 0. So the system is just, it has just potential energy. There is no kinetic energy at time t equals to 0. So for this reason, you can just consider a equals, you can calculate these things, but in this case, x as a function of time will correspond to some x naught cosine of omega t, and the momentum is just the derivative of this function, all right, because of the equation, right? That what follows, and this will correspond to x0 m omega 0 omega, all right? The omega here minus, because the derivative of a cosine is minus the sine function, and this will be just a solution for a mass at a position x naught at the time t equals to 0, and when it's left out from this position, it will oscillate. So if x naught is positive, the restoring force is to the left here, because x naught at time t equals to 0 is positive, this force is negative, it will try to restore to the equilibrium position, and the velocity or the momentum, if you divide it by the mass here, you get the velocity. The velocity will be to the left, and then because of inertia, you will pass from the equilibrium point and it will become negative. It will oscillate as a cosine function, and velocity at some point will be 0 again, and then the mass will become moving to the right side here. All right. But what is this frequency here? If you insert the solution into the equation, you can just differentiate this function twice to insert it here, and you'll find out that differentiating this function twice will get you an minus omega squared x of t. So if you insert the second order derivative of this function here, you'll have twice, or minus the omega squared, all right, minus the omega squared times the function again. And when you insert it here, you'll find something like minus omega squared plus k over m x as a function of time t equals to 0. There are two solutions: equilibrium, which means x of t is equal to 0 and the initial condition must be 0, or if x naught is distinct from 0, you'll need to have this thing here equal to 0, and this corresponds to omega equals to the square root of k over m. All right, so the oscillating frequency, the natural frequency of the oscillator is called the natural frequency, depends on the spring constant and the mass of the particle, just the two parameters in the system. All right, so you can rewrite the Hamiltonian, remember that, remembering that property, you can rewrite the Hamiltonian the following way. Remember that k over m is equal to omega squared. Then you can rewrite the spring constant as the mass of the particle times omega squared. And this comes from the original classical Hamiltonian, all right? So we will rewrite the Hamiltonian the following way. Momentum squared divided by twice the mass of the particle plus 1/2 m omega squared x squared. All right, this is kinetic energy, and this is potential. Right? If you plot potential energy, you'll find out u of x is a parabola. All right, it's a parabolic function. U of x is just equal to 1/2 m omega squared x squared is just a parabolic potential function. All right, this is what is meant by harmonic oscillator. It's the situation when the potential energy is described by a parabolic function. All right, so this is the Hamiltonian we are trying to deal with. So how do we quantize this problem? Quantizing the harmonic oscillator. just replace classical functions by operators. We are dealing with just one dimension, so this is minus I h bar, partial derivative with respect to the x variable, and we replace position by an operator, all right? But when acting at some position eigenstate or eigenket, it will produce just the eigenvalue, which is some x value, some position for that particle, all right? And it usually equations of motion in quantum mechanics are written in the basis of position, all right? So that's why usually you're already considering that momentum operator must be replaced by this differential operator with respect to position, and position operator is just replaced by its eigenvalue, all right, which is some x value at the given point, all right? But now let me discuss a little bit in what situation can we have a harmonic form for the Hamiltonian, all right, in a practical situation, all right? So consider, for instance, a molecule, all right? So you have a molecule. This is some coordinate here, say x coordinate. You have at some point, which can be to the right or to the left, all right? Doesn't matter. An object here, suppose this is some ion which has a very huge mass, all right? So it can be considered here as the rigid wall, all right? So this plays the role of a rigid wall. And here you can have an electron perhaps, or a smaller atom which have a mass m, and there is some spring constant here. All right, this would be some situation where this applies. But also we can just look at the potential energy in this problem. Let us look at some graph when you just approximate two objects, all right, to some distance, say r, the r distance, and the x distance is measured relative to some object here. But considering that the potential is a function of the distance here, all right, there is an equilibrium distance, all right, there is some equilibrium point. And when you have the two objects, suppose two atoms, these two atoms can be infinitely distant from each other. They do not see each other, and potential energy corresponding to the interaction of that system is nearly zero, right? It's nearly zero. But if you put them closer and closer together, it is expected if it will just form a molecule that the potential energy is reduced, because if it is raised by some mechanism, it will not be a favorable situation to form a molecule. All right, so nature always search for the most favorable situation, which corresponds to a minimum of the potential energy. So if it is to form a molecule, the potential energy will decrease to some minimum here, to some minimum, which corresponds to some minus u naught here, to some energy. And this corresponds to some equilibrium distance, some r naught, some equilibrium position, some equilibrium position which corresponds to the equilibrium distance between the two specimens or two elements or two objects which you are trying to connect. Suppose they are two hydrogen atoms, for instance. You can make them closer and closer, and at some point they will be together, all right? Because the potential energy favors the formation of a molecule. So initially you have an hydrogen atom here, hydrogen, and another hydrogen here. But when you put them close together, they will have a minimum of potential energy. But if you try to put them more closely together, the positive charges and the electrosphere will not favor anymore the formation of a closer contact. Suppose that the electrons are in an already favorable situation, but you try to approximate the ions closer together. So Coulombic repulsion between equal charges will raise the potential energy at, at, at some value which is higher than the equilibrium position. And if you try more and more to make these things closer, eventually you fuse two ions, but there is a huge potential barrier because at first you need to overcome the very high repulsion between positive electric charges. So the potential energy grows at very high values. But we are interested in the point of equilibrium, all right? So if the molecules or the atoms here are very distant from each other, they don't see each other, there are no interactions, potential energy is zero, all right? When you put them closer and closer together, they will interact, and at some point they will form a molecule. And this is the most favorable point in a diagram of potential energy. All right? But this is a minimum of energy, and any function which is well behaved, which is smooth, and all that stuff which we consider for well behaved functions, near the minimum, you can expand the potential in Taylor series around that point. So it is some u of r naught, which is the equilibrium point, plus the derivative of the potential calculated at that point, r minus r naught, plus 1/2 second order derivative of the potential calculated at some r naught, r minus r naught, which corresponds to the actual position, some actual position, and this is the equilibrium position. All right? And of course, if you have your particles here, you can find a center of mass and all that, but it doesn't matter. Suppose one of not two hydrogens, suppose one is much more massive, so that you can consider that the rigid wall and the other is it has a lower mass. All right, so just one can move, or you are considering the center of mass of the problem. All right, the motion, or perhaps the relative distance between these objects, and they can become closer and further apart from each other. They can oscillate here, and they can move in the neighborhood of the equilibrium point. All right, they can move. So the system will just oscillate here around the equilibrium point. Eventually, it can oscillate around the equilibrium point. Plus, it is a Taylor series. It goes to infinity. But if this distance is not too large, higher order terms will become vanishingly small. So you can just terminate your series round here to second order, right? Why first order doesn't matter? Just because a simple fact. The derivative of the potential here exactly at the minimum is equal to zero because it's a minimum. So the first order derivative is zero. All right? And second order derivative is positive because it's a minimum. So near to a minimum, the second order derivative is positive. So this is a positive value. And this x, this distance here, r minus r naught, I can call it x. The slight difference from the equilibrium. It's the difference between the actual distance of the objects and the distance at the equilibrium point. So for an hydrogen molecule, you have two hydrogen atoms at an equilibrium distance, but you can try to pull them apart, and there will be a restoring force, which has, from first principles, Coulombic or electrostatic uh, or electromagnetic origin, but the system tried to put the atoms, restore the atoms to the equilibrium position. And if you try to squish them together, there will be a repulsive force, which corresponds to a restoring force, which will try to put the system back to the equilibrium position. So this distance here, this difference between the actual position and the equilibrium position, we will call it x. All right? This way, near the equilibrium, your potential energy will become a function of some x, which corresponds to the difference. So this is a Taylor series. And the energy of the equilibrium point here is some minus u naught, right? So it is a constant here plus 1/2 of the second order derivative evaluated at that point of equilibrium times x squared, all right? Because this is just zero, right? Because you're considering the equilibrium point, near the equilibrium point. In this way, you'll have a Hamiltonian, which corresponds to some kinetic energy, all right? So this is the kinetic term, and the potential energy in general, and you can move your energy scale around u0, so you can just rewrite the Hamiltonian with respect to that value plus some u0 there, all right, because you're replacing this potential here, which corresponds to a new Hamiltonian. Okay, the energy scale you can define from what value of energy you are measuring the other energies. So this is just a constant. You can, in this scenario, you can put it to be zero, right? But it doesn't matter because you just add some constant to the Hamiltonian and it is eliminated, all right? Plus, so you have a kinetic term plus 1/2 second order derivative x naught. And this you can write, because it's just a constant, you can write just as some mass times omega squared. So m omega squared is just related to the second order derivative of the potential in this scenario with respect to position. All right? And this is it. So your Hamiltonian will correspond to a harmonic oscillator. This half factor was already there, and you have this thing here. So I'm trying to justify a little bit when or where this Hamiltonian would appear in a practical quantum mechanical problem. It can appear, it appears in the case, for instance, of a binding between two atoms, and you are trying to study vibrational modes near the equilibrium point. This is a quantum mechanical problem. You are not trying to find out what are the energy levels of the atoms or the molecule as a whole, because this corresponds to some minimum of energy. It is the most stable position, but the atoms in a molecule can vibrate around the equilibrium point, and this is explained, at least as a first approximation, by a harmonic oscillator, all right? Well, that being said, we can now discuss the quantization of the problem, but using Dirac's method, all right? Dirac's operator method. Of course, you can now have this Hamiltonian for the system, which corresponds to momentum operator divided by twice the mass plus 1/2 m omega squared. The position operator, if I represent this thing here in the position basis, this operator corresponds to minus I h bar, the spatial derivative, and this applied to h to some psi function is equal to E times that function. It corresponds to the eigenvalue problem. You need to solve the eigenvalue problem. If you project out this problem into the space, into the basis of position, this is just psi of x, and if you plug in the position, you project out the equation to the position of basis, the basis of position, sorry, you'll find out the following equation: minus h bar squared divided by twice the mass, second derivative with respect to x of psi of x, plus 1/2 mass omega squared psi of x is equal to energy psi of x. It is a differential equation. You need to solve for that equation, and it's very complicated to solve that equation, or it's already done. But Dirac devised a more, perhaps a more interesting method, more intuitive. It's not, but it's more interesting, more smart method of solution of this equation. All right. So just look at the form of the Hamiltonian. All right. And remember the following fact: X with P, the operators in quantum mechanics, they don't commute. They are equal to I h bar, which is the canonical commutation relation. Of course, the operators with themselves commute. Right? It's easy to show that, right? These are the canonical commutation relations. But look at the following form here. If you would just make m and omega equal to 1, or you renormalize the constant, the form of the Hamiltonian would be p squared divided by 2, if you proper normalize the quantities here, plus x squared divided by 2. So 1/2 of p squared plus x squared. If they were just classical functions, they could be written in the following way. And the order doesn't matter because in the classical world, that doesn't matter. So it could be written this way: x minus a times minus I times p, x plus I times p. You can do the calculations here. If x and p were classical functions, properly normalized, to get rid of these terms here, all right? So if you get rid of that spurious terms here, which complicates equations, so h bar, m, all the constants just pollute your equation, but you can just renormalize distance and momentum and all that. So you could, in appropriate units in this problem, rewrite the system in the following way. You would find this kind of form. You can just separate the squared quantities here in the following form. So notice that this is just the square of the first term, which produces this term here, and the square of the second, but now you have a minus here, and minus the square of the second, so you have an imaginary unit here, and you will find out positive. All right, you can multiply all the things here, and that will be fine. All right, if they were classical. But Dirac, noticing these facts here, and I don't know if he looked at something like this, but it seems pretty nice to look at the following form here. Just can put the Hamiltonian in a form of first order differential operators, because P appears just at order 1 here. Dirac defined the following operators. They are so-called creation and annihilation operators, or ladder operators. You can define an operator A, all right? It's an operator in quantum mechanics. And to be very precise, you cannot just separate things like in classical world, but you can try and look at what happens if you define this operator here just like this thing, m omega divided by the h bar. So this is the normalizing which is needed, all right? It's normalized by the Planck constant, x plus I operator p. All right, x is also an operator in quantum mechanics, and the H dagger, which is the complex conjugate of this operator in quantum mechanics. Remember, observables: x is equal to x dagger, p is equal to p dagger. It must be, because they are just observables, so observables are Hermitian, right? So the H dagger corresponds to just taking the complex conjugate of this operator here. It will become minus I times P, right? It's just changing the sign of the imaginary unit, all right? Well, these two operators, the Hamiltonian somehow must be proportional to the product of A dagger A. In what order, we will see, all right? But it must be proportional to this thing, all right? But now I must take into account that x and p do not commute with each other, all right? They don't commute. But the Hamiltonian can be written as proportional to that product, right? Why not trying the other way around? You could do that, but in the end, you can replace things and put in the following order, which is more interesting for now. All right. Okay. Now let us see what happens if we define these two operators. Right. Let us see what happens for the product. A dagger times A. They are two operators. You multiply A dagger times A. In that order, you cannot reverse the order for now. You'll have, because both of them have this, sorry, I forgot the factor of 2 here. Both have this normalizing constants, which are just depending on the mass, the natural frequency, and the Planck constant. You'll find out the square root squared. So m omega divided by twice the h bar. And you'll find out that this multiply that, you get an x squared factor. Oh, this is normalized by m omega because you need to have same units for the operator. So from dimensional analysis, you can see that if you divide momentum by mass times frequency, just corresponds to position. Well, we can do that because momentum is mass times velocity. If we divide this thing, momentum is mass times velocity. If we divide this by m omega, it corresponds to, in a dimensional analysis, all right, mass times frequency, angular frequency. So mass gets cancelled out, and velocity, which would be something like meters per second, divided by 1/second or radians per second, becomes meters. So dimensional analysis will show you that you need to mix position with momentum, divide by some constant, which has units of mass times angular frequency, and it's better to use the constants which we already have, all right? So m omega divided by twice the h bar, so we have x squared. The second factor, which is p times p, I times minus I, you'll find out minus I squared is a plus, so plus p squared divided by m squared omega squared, but it just doesn't end at that point because I have the products. This x, so plus the imaginary, this x times that p divided by m omega. So this x times that p, in that order, h dagger first. And I will have this, which corresponds to minus I. This term here multiplies that, all right? Px divided by m omega, all right? So we cannot just cancel out these things because now we have quantum mechanical operators and this factor here. So the h dagger A can be replaced or can be written as the following equation: x squared plus p squared divided by m squared omega squared. And this, if I put the imaginary factor as a common factor and this m omega as a common factor, we'll have the commutator of x and p. All right, the commutator here. And this factor there, we already encountered. It is given by the commutator, and it is the imaginary factor times the h bar, all right? So you can replace by imaginary times h bar. And now, what you can rewrite, h dagger times A, the product of these two operators here. I guess you can read h dagger times A dagger times A, which is what we will call a creation operator, the A dagger, and the A will be an annihilation operator or destruction operator, all right? Will become M omega divided by twice the h bar x squared plus p squared divided by m squared omega squared. This imaginary unit here with this imaginary unit you will produce a minus 1 h bar divided by m omega. All right, this is it. So remember these definitions here because I will need to erase. Remember this, right? But remember the Hamiltonian has the form p squared divided by twice the mass plus m omega squared x squared divided by the number 2. And this h dagger a corresponds to 1 over h bar. We can just divide everything by this h bar. If I insert here, notice some omega here and some squared here, because omega squared divided by omega just cancels out, and I'll have the original factor of omega in the in the numerator here. So I will have h bar omega, all right, this h bar omega, and the rest I will multiply all the factors there. So m omega squared times x squared divided by 2, all right, plus omega squared cancels out this factor, so I'll have p squared divided by twice a mass here in the numerator cancels out one factor of mass here, so it will become divided by twice the mass minus. Now we are multiplying uh, everything here by m omega squared divided by 2 by this factor here. So m omega cancels out. We'll find out h bar omega divided by 2. All right. And notice this is just the Hamiltonian. This is just the Hamiltonian. So a dagger a corresponds to the Hamiltonian divided by h bar omega minus 1/2. And you can write the Hamiltonian the following way. If you isolate the Hamiltonian, you can multiply everything by h bar omega. You can just plug this 1/2 together with you can put this 1/2 together with this a dagger a. So we'll find out h bar omega times a dagger a plus 1/2. All right, this is it. This is it. This is what we can find for defining the operators that way. All right. Okay. Now let us see something here. Let me erase what I have written here. So just remember this fact. Right? Remember that. Remember that fact. But now we can calculate some aspects of the algebra of these operators. You can calculate the commutator of A and H dagger, and this will be given by the commutator of M omega divided by twice the H bar X plus I P divided by M omega, which corresponds to the A, comma here m omega divided by twice the h bar x minus I momentum divided by m omega, and you'll find out some quantities here. Both terms have this factor which gets squared, so m omega divided by twice the h bar, and you will find out four commutators: x with x minus I x with p divided by m omega plus I commutator of p with x divided by m omega, this term times that, it's a commutator, all right, and plus momentum commutated with itself, and you get the squared factor there, but that doesn't matter because this is zero, that is also zero. Momentum commutates with itself, position commutates with itself. This is I h bar. If you reverse the order in a commutator, you get a minus sign. You can show that. And in this way, we will have the following. So look, m omega just cancels out with this factor here. So this h bar also cancels out this h bar here. You have the inverse factor here, h bar divided by m omega divided by h bar. So you get 1/2. And this term here will correspond to the minus the imaginary times the imaginary, which is 1, plus this is minus the imaginary, but times plus the imaginary, which corresponds to another 1. So we'll find 1, the identity matrix. All right, it corresponds to the identity matrix. So A dagger A commutated in this order is just 1, right? You can show also that a commutator of the operator A with itself is 0, and of course A dagger with itself is also 0. But you don't even need to worry about that because any operator commutates with itself. All right, it's just matrix algebra. So this is the important factor. Commutator of A with A dagger corresponds to 1. All right, remember that. It was we already we just have shown that fact. All right, this is a very important result. Now you can just use the Hamiltonian as h bar omega A dagger A plus 1/2 here. This term 1/2 will be known as the vacuum energy or the 0-point energy of the system, right? And we need to find out what is the eigenvalues and eigenvectors here. So I need to use that equation to find out what happens. But notice that I can use some facts here. Remember that A is equal to square root m omega divided by twice the h bar x plus I p divided by m omega. So that is just a differential operator when acting on the basis of space, all right? And now I can find for this problem, which has a positive definite Hamiltonian, because it's a sum of squares, we'll find out that when you apply this to some, let us call the zero function, psi 0, which corresponds to the lowest level, it is corresponding to h bar omega A dagger A plus h bar omega divided by 2 applied to that psi 0. It corresponds to the energy E0 times that function. All right, this is what we are trying to determine here the ground state function. And this ground state function, notice this is a positive definite operator, so this will be higher than zero eventually, at least zero, and this becomes the lowest energy level. We already found the lowest energy level. Why is that? Because if you take the averages of the Hamiltonian with any given state, you'll find out that the energies in the system is positive. All right, it's positive because it's p squared and x squared. The average of squared operators are always positive. It's a from matrix algebra. It's a fundamental result. So this operator will become always positive, and this operator is at least zero. So we'll find out applying to that the zero, which corresponds to the lowest level, because any other value will be positive. All right. This way, because this is also a Hermitian operator which corresponds to, there is a positivity, I guess, a positivity condition here. So we'll trying to find out H Jagger A applied to psi 0 equals to 0. All right, equals to 0. Why is that? Because this way we have the ground state with this energy here, H bar omega divided by 2. Right? This is the ground state of our system. Notice that for a quantum harmonic oscillator, a quantized harmonic oscillator, there is a lowest possible energy which corresponds to this value. For a classical harmonic oscillator, the Hamiltonian can produce zero. Just plug in the equilibrium condition, initial conditions all equal to zero, momentum zero, position zero, equilibrium will produce zero for the energy of a classical harmonic oscillator. But for a quantum harmonic oscillator, there is a minimum energy which corresponds to this value. So this is the 0 point energy, or the vacuum energy for the harmonic oscillator. All right, so we are trying to apply this operator to the function here and produce zero, nothing. And what remains is this h bar omega divided by 2 psi 0, which is equal to this energy, and that's the fact here. So we are trying to solve this problem here now. All right, we are trying to solve for the lowest level energy. Let us see what comes out. If both operators can be represented as differential operators, it just suffices to do the job that A operating on this vacuum eigenstate. So let us call this psi 0 just 0, which is the vacuum. All right, this is the vacuum of the problem. When this operates to the vacuum, it just destroys the vacuum. That's why it's called an annihilation operator. It annihilates things. And this, in the basis of position, if you project out this equation into position basis, will produce a operator times the psi naught function, this differential operator times psi naught function, which depends on x equals to 0. And now let's plug in the operator to be precise. But now remember that this common factor doesn't matter. You can just get rid of it. All right, so it's just because you have 0 in the right hand side of the equation, this is just a constant. Just forget about the constant. You'll find out x plus the imaginary divided by m omega, the momentum operator operating on the function psi naught equals to 0. And now you can plug in just x plus, remember, momentum is minus I h bar partial derivative. So this minus with this plus I will give you plus h bar divided by m omega. Notice this factor appearing here, which is to the minus 1 appears here also. The partial derivative applied to this function equal to 0. All right, equal to 0. This is a first order differential equation. It's very easy to solve. Now we have replaced our second order equation in this Dirac method by a first order equation. Now you can see that d psi 0 dx, if you multiply things here, you can rewrite it as minus x divided by h bar over m omega, right? Divided by this factor, we eliminate this factor, psi naught of x. And this can be promptly solved if you divided everything by psi naught here, and you can multiply by dx, integrate out the solution. It's easily calculated. Psi naught of x, just a few steps here. The psi naught divided by psi naught is equal to minus x divided by this constant, m omega dx. You integrate both sides, you find out a logarithm, a natural logarithm here, and here you'll find out x squared divided by 2. So the solution has the following form: some constant a times the exponential of minus x squared divided by twice some x naught squared. And this x naught squared is just the square root of this constant here, h bar over m omega. All right, this has units of length. All right, and this just corresponds to the width of the Gaussian. Oh, what we have found, a Gaussian. So we can readily find this a constant here. Why is that? Because the normalization of the state, now from minus infinity to infinity, dx must be 1. The probability of finding something there must be 1. So you can find out what this value of a is. We already done that previously. All right, so you can do the math to find out this thing here. But the fundamental state of a harmonic oscillator in quantum mechanics has a non-zero energy. It has a minimum energy, but it's non-zero, and it is described by a probability which is a normal distribution, all right, or a Gaussian. This is a very important fact here. So the fundamental state corresponds to a Gaussian, psi naught represented in the basis of position, which is a Gaussian. This x0 is just a function of the Planck constant and mass and natural frequency of the oscillator, and the energy is just a function half the h bar omega, which is just Planck's relation relating energy to frequency. All right. Well, we have found the properties of the fundamental state. Now let us see if we can find out something else from that point, right? Just remember that. Well, let us try another state, which we will call 1, or if you prefer, psi 1, right? Which corresponds to some operator, the other operator, operating on psi 0 here, all right? We will operate the A dagger on the vacuum state, the 0 state, and we will try to find out what it does to the system. First, let us see if this proposed state, proposed state, which corresponds to the other operator operating on the vacuum state, the minimum energy state. Let us see what it does. Well, I am trying to find out if it satisfies the eigenvalue and eigenvector. Eigenvalue and eigenvector equation. It must satisfy this thing here, all right? So remember, the E naught energy, which is the vacuum energy or the fundamental state energy, corresponds to h bar omega divided by 2. Let us see if this proposed state here also satisfy. I At this point I don't know, but I'll find out if I apply the Hamiltonian, which corresponds to h bar omega a dagger a plus 1/2 to the proposed state. So let us do that. Let us do and see what comes out from that equation. Let us see what comes out, right? So H, the Hamiltonian applied to A dagger psi 0, because I can write the proposed state by this operator method here as an A dagger applied to the fundamental state. I will always forget the hat in the operators, but just remember they are operators, right? I'm anticipating this is a creation operator, all right? So let us see what happens here. We'll have h bar omega, a dagger a plus 1/2 times a dagger psi naught. If we applied without this operator, we'll produce this thing applied to that 0, and this thing h bar omega over 2. It's just the energy of fundamental state. So of course, the first part, which is just h bar omega over 2, which is the vacuum energy applied to the state psi 1, is already there because a dagger psi 0 is just that. But we need to evaluate this thing here. A dagger applied to psi naught. All right, we need to evaluate this thing here. Just remember that matrices, this is the state psi 1, matrices can be associated. Eventually, you cannot commute matrices, but they can be associated in any order we want. So let us see what is this term here. A dagger, a dagger, right? A dagger, a dagger corresponds to, let us perform a commutator here, all right, between these two factors. So remember, the commutator of a and a dagger is just 1, which means a dagger minus a dagger a. This corresponds to 1. So I can write this thing here, a dagger a as, if I just pick up this term here, I get 1 plus this factor here, a dagger a. So I will have a dagger times 1 plus a dagger a. All right? This is what we have for this product of 3 factors here. And this way, when we apply the Hamiltonian to the state psi 1, okay, we will have h bar omega times a dagger plus a dagger, a, all right? Because we are rewriting, we are recollecting the terms here and writing this the following way, because we can use the commutator relation for the operators, the ladder operators, as Dirac called them, psi naught. I'm just rearranging this in the following form here, just you to remember that. I'm, instead of picking up the a dagger a applied to psi 1, I just rewritten the psi 1 as a dagger psi 0, and I am now multiplying these things here to see if I can find some more intuitive or more easy calculable results. All right, so we have here h bar, oh, but I cannot forget the other term, plus h bar omega divided by 2 times the state psi 1, which was already there. So this term here is what corresponds to a dagger, a dagger. All right. Now, remember that when this factor here operates on psi 0, it destructs the vacuum. This a applied to psi 0 is just 0. So I don't need to worry about these other two products, because this a applied to psi 0 is just 0. And this a applied to psi 0 just corresponds to the psi 1. And this way, I have a constant which corresponds to 3/2 of h bar omega times psi 1. And now I have found that psi 1 is also an eigenstate of the Hamiltonian, but with energy, the E1 energy corresponding to 3/2 h bar omega, but it's just h bar omega 1 plus 1/2. And remember, the Hamiltonian has the following form: h bar omega a dagger a plus 1/2. And therefore, I know that this operator operating on the state psi 1 just produces 1, right? So this is 3/2. If now you insert another solution, of the form some psi 2 corresponding to a dagger psi 0, which is a dagger applied to psi 1, you'll find out this also satisfies the eigenvalue equation, but this E2 energy corresponds to 5/2 of h bar omega, or h bar omega divided by nothing here, h bar omega 2 plus 1/2. So notice this psi 2 state corresponds to the vacuum energy plus the eigenvalue of this operator, which is 2. So a dagger a operating on states which I'll call psi of n, some subindex n, will produce an integer n times that state. And that state, psi subindex n, corresponds to application n times to the vacuum state. All right? I am not properly normalizing the states, all right? I am just trying to induce the results here. So there are normalization factors which I am just letting it out for now. I am not interested in finding out what they are right now. But notice that this operator here can be called a number operator. And this representation of the problem is the number representation. So I have number representation whose states are given by some n, some integer n, and these states are eigenstates of this operator, A dagger A, with eigenvalue n. All right, and these n's can be 0, 1, 2, 3, and da 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 da, so on. The fundamental state is 0. The next state is 1, 2, 3 are integers, right? And the application of this operator to some of that states are given or produce the eigenvalue, which is an integer number, all right? And the states n are proportional, apart from some normalization, are proportional to the application of this operator, which corresponds to some creation, n times to the vacuum state. All right, the vacuum state is the lowest energy level. You can apply this operator n times. 0 times gives you the vacuum, 1 times the first excited state, twice the level 2, and so on. And this corresponds to the idea promoted by Planck originally, that oscillators, harmonic oscillators, are quantized in energy levels of h bar omega. So you can think that the A dagger operator, creates a particle of energy h bar omega. It's a quantum of energy. So a particle, in that sense, is created by that operator. And the Hamiltonian, which has, in this case, this form, when applied to an n state, corresponds to n particles of energy h bar omega plus 1/2. All right? And this 1/2 is the vacuum state, n equals to 0. And you can find out all the states represented as a position functions, in this case for the harmonic oscillator, just picking up the Gaussian. You need to proper normalize all the functions. So the Gaussian, you need to normalize them or to renormalize them if the normalization is not given here. So this operator corresponds to m omega divided by twice the h bar, x minus I, the momentum operator, divided by m omega. You have this function, and you can apply this differential operator, because P here is just a differential operator. You can apply this operator successively to the vacuum state, and you'll find out the first application, the psi1 of x, so A dagger to psi0 will give you a psi1, and you can normalize that to having squared integrated modulus of the function. You can make it to be 1, because probabilistic interpretation needs all the states to be normalized to 1. So this state psi1 must be normalized to 1, and all that is equal to 1, or any n level must be normalized to 1. So you can check out the normalization, of course. But when you apply once this operator to the vacuum function, you get the first function as a function of position. The second, apply again, you'll find psi2, apply again psi3, and so you can construct all the solutions for the harmonic oscillator for the differential equation, which corresponds to something called the Hermite polynomials. Okay, you'll find out the Hermite polynomials. Right? These are linked to the solutions here. All right. Well, this is what we have when we apply a dagger a to any level here. It corresponds to having n particles with energy h bar omega plus 1/2, which is the vacuum state, no particles, but it has some minimum energy. This 1/2 is what produces some problems when you quantize a field, because a field can be considered as a set of harmonic oscillators. There are an infinite set of harmonic oscillators, so you must add up the energies of the vacuum for an infinite number of degrees of freedom, and this produces an infinite value. But you can subtract the vacuum and you can work with that, all right? But that's beyond the scope of this present lecture, all right? But this half, when quantizing more than one oscillator in a field quantization, it produces some infinities, which are not desirable in a quantum, in a physical theory, right? Well, therefore, you have in the energy spectrum something like this. H bar omega over 2 is the vacuum, right? 3/2 h bar omega, which corresponds to the n equals to 1. So this is the energy levels. 5/2, 7/2, which corresponds to 0, 1, 2, 3, and go on forever. Number of particles in the system. These particles in this problem are just the pseudo particles, all right? Just you can interpret the solution as having n particles producing the energy. In fact, you have the solution for one system which oscillates around some harmonic oscillator potential, but you can interpret the energy states as creating, as you apply the A dagger, as creating levels with one quantum, zero quantums. So this is the vacuum energy, one quantum, 2, 3, 4, and so on and so forth. Right? You can calculate the algebra for all the things like A commutated with the N operator. Just calculate that. You can calculate A dagger with N. Just calculate that. What do you find in these cases? Then the number operator is just A dagger A. So the eigenvalues of this operator are integers. When this operator acts to some n level, it produces the number n times n. So notice the following. Notice the following thing. If you calculate the average of this operator, of course, it will produce n. All right? It produces n. Because when you apply this to that, it's just an eigenvalue equation. But also remember that A to n dagger is the bra of n and the dagger of this operator, and they are not Hermitian. A and A dagger are not Hermitian operators. This is a very important thing. And just remember that if you apply A dagger to some n you produce some n plus 1 state. When you apply A to n, you produce something proportional to n minus 1. This can be easily demonstrated. All right. So remember this equation here. Remember this equation and remember that fact. So just to find out what the action really is with normalization of the A and the A dagger operators. Look that if we apply A to some state n, all right, I can rewrite that in the following way. A commutated with A dagger, which is just 1 here. I am putting 1 in front of the equation, so it just does not change anything here. And I'll find out the following thing here. But just remember, A dagger A to some level, say n, corresponds to n, and repeat the eigenvector. So these states are eigenstates of number, all right? So let us do the math here. A applied to some n corresponds to A dagger n, A dagger A n, minus A dagger A applied to n. All right? But notice now, perhaps I need to plug in the one here. All right? 1A, and here the commutator. All right? This is what I'm doing. This is better. So I'll have, no, sorry, that was right. A dagger here, and this is A here. All right, this is the one. Sorry, I was going to a more difficult way if I plug in the one here. Right? If you insert the one at the wrong place, you just have to work a little bit more. Right? So, but now that's correct. So we have A dagger A dagger A dagger A, because this commutator is just A dagger minus A dagger A. So A, which we already have here, A dagger times this A minus this term here, A dagger A times the A which was already there. And in this case, just look at, if I apply the operator here, I will have A times n is equal to n A times n minus A dagger A times n, which I will recollect this way. I can just associate matrices. So this is the state, which I don't know what it is already. Yet. Sorry. I don't know yet. But you'll find out. Now, if I put the number operator here in front of the equation, so I can just pass it to the left and this term to the right, I will find out that A dagger A applied to this new function here corresponds to this n minus 1, because I am bringing it to the right, n minus 1 A to the n. So it is because of the commutation relations, because of the form the operators are defined, it is necessary that the state A n is another eigenstate of the number operator, because remember n is this A dagger A is a number operator with eigenvalue n minus 1. So if this is true, when you apply this operator to some state n, it will be proportional to the state n minus 1. All right, this must be necessary to, it's proportional to state n minus 1. Why is that? Because when you apply the number operator to a state constructed that way, the annihilation, I am already saying annihilation operator applied to n, it produces a state, an eigenstate of number, because it repeats itself here as an eigenvector, but with eigenvalue n minus 1. And this is also an integer, and this is the eigenvector corresponding to n minus 1. The number operator operating to n minus 1, no matter the proportionality factor here, because it appears here and there, corresponds to an eigenstate which has an eigenvalue n minus 1. So the number operator, so the A operator, as we are trying to just identify, is annihilation operator, because when it applies to an n state, it produces a state with one quantum less, n minus 1 quanta of the field, or of the energy. Sorry. And you also can perform for the H dagger, but the H dagger operating to n, we already know what it is because of the form these things are constructed. We already know it is proportional to some state with one level more, because what we are constructing is the state 1 is the application to a zero state. The state 2 is application to state 1, and all that. So this operator creates one quantum of energy. So it, in the sense of particles, if we are trying to interpret as creating some particle of energy h bar omega, it creates one particle and this annihilates one particle in the system. But what is the normalization? To finish with this explanation, just remember that n, a dagger, a, n, this is a number operator. It corresponds to just n, all right? But now you know that you can, since you can just separate the form. You can separate the equation this way, because matrices can be just associated. This is a matrix operator, this is a matrix operator, this is a vector, which is an eigenvector of this product. But now I'm separating, associating this way. I know this is equal to n, something here, which is n minus 1, and something here, which is the dagger of this state, which is something like n minus 1. All right? So what must be the action of the annihilation operator on a state of n quanta? It must be proportional to n minus 1. But now remember that this product here is just like the modulus of this vector. So I can, since this state is normalized to unity, because the A applied to this thing here produces some state like that, n minus 1, but I don't know the proportionality. Notice that this is the modulus, this product here is just the modulus of that action squared. So if I take the square root of that, I will find out a square root of n and this is the proportionality factor. All right, you can do the math. So A times n, A dagger times n to the left, because this is the bra, this is the cat, corresponds to square root of n times n minus 1 when acting there, and square root of n when acting to the left, n minus 1, and this is just n, because this state is normalized. Square root of n times square root of n gives n, which is the necessary result. So when you act on the number space with A acting to some n is equal to square root of n, and produces the state with one quantum of energy less than the previous state. It changes the state by one unity of h bar omega in terms of energy. Also, you can perform the math and, and just act by creating something. But now see that I can apply this to the state A dagger A to n produces n and repeats the eigenvalue. But notice that I can apply, associate, this is the number operator, I can associate in a different manner, right? I can associate this in a different manner, this way here, all right? And this produces the square root of n, n minus 1, this action here, and I need to have A dagger. So A dagger operating on that thing, just to have this result here, I need to have n, must produce some square root of n times raising by one unity this thing here. So here I have n minus 1, the proportionality factor of A dagger operating on something like that. This square root was already there. So I need to find out what is this thing here, what is this object. It must produce this n, which is here. I already have a square root of n, and I must produce another square root of n. So this is n, and repeats the state. So when A dagger applies to a state n minus 1, it produces the state n with the proportionality factor square root of n. All right. This way, if you just consider n here, some n minus 1 is equal to some n, capital N, A dagger applied to some capital N is equal to the square root of this n is the capital N plus 1. All right, capital N plus 1, and you raise this by 1 unit. It is more elegant to rewrite the equation this way. This way, we have the action of A to the number state n is equal to square root of n times that state minus 1. It's not an eigenvector of A. A dagger applied to some n is the square root of n plus 1, n plus 1. Notice the distinction. And when you apply in sequence, you can show that, we already used that, is the number times the eigenvector. These vectors here, these eigencats, are eigenstates of number. All right, this is number representation. Of course, commutations or commutation relations are already known. And this is the basis for using number operator when quantizing fields, when just working with collective oscillations, when trying to quantize fields, we need these operators, but the origin, we can see it has roots in the harmonic oscillator, all right? That's a very fundamental problem in quantum mechanics. These operator methods were introduced by Dirac, all right? And as a final comment, since we were dealing with harmonic oscillator, just remember that A is equal to this object here. These are operators. Sorry, twice H bar, twice H bar. And now you can calculate X from these operators here. And you now, using operators, the annihilation and creation operators, you can perform all the calculations of averages of X, X squared, momentum squared, and all that, because you can just add up these two equations here. So you have A dagger plus A and divided by some constant. You will have twice this value here, so the twice can enter the square root. So the H bar divided by twice m omega, I guess, if I did it properly. But it's just adding up these two equations, and the momentum is proportional to the difference between A and H dagger, but is now proportional to some imaginary unit here. All right, you need to find out what the proportionality constant is. All right, it's left as an exercise, so you can perform the calculations. Also, some term depending on m omega will appear here. All right, so square root of some factors there, you can find out the factors. All right, so now you can derive the equations of motion. So I will left as exercises. Find the equations of motion for A and A dagger in Heisenberg picture. All right, it's pretty easy. You have the Hamiltonian. You have the commutators, and of course, you need just to calculate something like this. And that's why you need to calculate the commutator of this operator with the number operators. All right, you can calculate that. Also, you can calculate the equations of motion for the A dagger. So that's why you need to find out, and you can solve these equations. It's really easy. Solve the equations, and in the end, for the state, an arbitrary state n, right? Find x as a function of time, momentum as a function of time, because you already have this as a function of time. It's just these operators as functions of time. So you'll find out what they really what they look like in a Heisenberg picture. And in the end, to complete, calculate delta x, delta p, which means you need to calculate the averages of x, the average of x squared momentum squared using the same state n, and you will replace x and p by representations in terms of these operators. These operators, you already know what they do when acting on the number eigenstates. And hope you can find out. Sakurai has some problems related to that. Hope you can find out the solutions. It's not that hard to find out, but I will left as an exercise. I guess I just discussed. I just used a little bit more time than I expected at first when providing this lecture. So I guess an hour and a half or more than that, and I don't have time to do more calculations, but you can find out. You can calculate these things. Hope you enjoyed. So bye bye. See you next time.